Okay, this is Physics 1B for September 9th. Today we're going to be talking about the topics that are written here. We're going to do a couple fluid dynamics problems, and we'll talk about viscosity and turbulence as well. One thing people had mentioned before was that the volume on my YouTube videos was kind of low, so I've attempted to fix that. If you don't notice any change, let me know. But they should seem louder. Did anyone have that problem before, that you thought the YouTube videos were too low? Or have any of you even watched the YouTube videos? It's okay if not. It was on the list. Okay. I think it should be better now. But you guys tell me. If you go and watch those videos after today and it's still bad, let me know. But it should be fixed. Okay, so someone's typing something. I'm going to let them finish typing before we get started. No? Okay. All right, so our last meeting was, almost 10 days ago, I believe. So let's just do a quick review of what we learned. So we learned about fluid flow, and we talked specifically about fluids that are both incompressible, which means they can't be compressed, and fluids that flow basically without friction. We didn't really worry about viscosity or friction. And we were also specifically looking at fluids that flowed laminarly. I don't know if that's the right way to put that, but they exhibited laminar flow. And with fluids like that, we developed a couple equations that we can use to describe some things. So one of the equations was called the continuity equation. And this equation said that if I have a pipe and it has a cross-sectional area that changes in some way, I can relate the area of the pipe to the velocity of flow through the pipe. And this would be for a fluid whose density doesn't change. So again, incompressible. And this is the relationship, that the area of the pipe multiplied by the velocity of flow within the pipe is a constant. And this quantity, A times V, is called the volume flow rate, basically. Okay? You could write it as dV dt, where V represents volume on the left side here, and velocity on the right-hand side here. Volume flow rate. It has units of feet cubed per second, or meters cubed per second, or liters per second, okay? The other equation that we got is called Bernoulli's equation. I'll just say Bernoulli's. And that equation says that the quantity, if I take the pressure of the fluid flow, and I add to that a term that kind of looks a little bit like kinetic energy, and I add to that a term that looks a little bit like potential energy, that this quantity is a constant for fluid that's flowing in a system. And we can use these two equations here to solve quite a few problems. We already solved one problem with it, involving a tank that had gasoline flowing out of it. And we're going to use it now to solve this problem on the left right here about water pressure in the home. So let's read the problem. It says water enters a house. Let's see, is this... I probably need to make this just a little bit bigger. There we go. So water enters a house through a pipe with an inside diameter of 2 centimeters. So that's the water's coming in down here at the bottom. At an absolute pressure of 4 times 10 to the 5 pascals, which is about 4 atmospheres. A 1 centimeter diameter pipe leads to the second floor bathroom that's 5 meters above. So this pipe, it goes up to here and then up to here. And it says that the pipe here has a 1 centimeter diameter. So the pipe down here is a little thicker. It made it blurry. Is it okay now? Well, but everybody else had the same thing, Miaras. It had to be me. It's still blurry? I'm gonna stop the stream and I'm gonna restart it. Is that okay? Okay, I restarted the stream. You should be able to rejoin. You guys let me know if it's still blurry. I'll slow down until it's not blurry anymore. Yeah, the recording's done locally, so 100% it'll be good. Is it clear enough that you can read the words? All right, so it was just a temporary like internet hiccup on my side, probably. Well, I know for a fact that my internet has like really, really bad inconsistencies, so I wouldn't doubt that it had something to do with that too, other than just being Discord. But I know what you're talking about. I've definitely seen Discord streams where that happens. All right, well, let's keep going. So this is the problem. We were still reading it. So when the flow speed at the inlet pipe here is 1.5 meters per second, find the flow speed, pressure, and volume flow rate in the bathroom, which would be up here, basically. So I kind of would like for you guys to try to solve this yourself. We have the two equations we need up here. Yeah. There's a lot of other stuff in this picture, but really the only thing you need to understand is that you basically have a setup like, I would put it like this. The fluid comes into a pipe down here, right? And this pipe has a diameter of 2 centimeters. So this is 2 centimeters. You've got fluid flowing through that, and then it flows up to another pipe, which is a skinnier pipe. So this one has a diameter here that's 1 centimeter. And we've got our fluid, and it's flowing in here. They give us the flow speed into the pipe here, so we know what the velocity of the water here is. You can call it V1, and it's given to be 1.5 meters per second. The other thing we know is that it's a 5 meter upward distance to get from this pipe to this pipe here. So we can just indicate on here that this is 5 meters. We'll say from the center to the center. And the question is, you also know the pressure over here as well. So you also know the pressure down here. That's given right here. So you're supposed to figure out at the top what the values of the pressure in the water is, as well as the velocity that the water comes out here. Call it V2. And what else? The volume flow rate. So the volume flow rate would be basically just AV. All right, I'm just going to give you guys like, I don't know how long it's going to take. Maybe it'll take 3 minutes or 5 minutes. I'll give you guys like 3 minutes and see how you're doing at 10:17. See if you can solve this problem by using the equations above. You have any questions? Okay, that was like 4 minutes. Is that enough time? Did you guys get an answer for either of these yet? You want to just type any answers you got in the chat? Anybody else? Okay, some other people are typing, but... Okay, I'm pretty sure that answer's right from my memory. What about the pressure? Okay, I'll give you guys a few more minutes. Looks like people are tending to agree on the pressure. Numbers are a little bit different. Okay, let's work through this problem on the screen. It seems like most everybody's getting the answers at least close to right. So, what do we have here? It seems like most people solved for the velocity first. That makes sense because we can directly solve for the velocity from this equation, right? Is that what you guys did? Okay. So let's do that real quick. So we can just rearrange it immediately and say V2 is going to be equal to A1 over A2 times velocity 1. Let's see, area 1 is the one that has a diameter of 2 centimeters. That means it's going to have a radius of half a centimeter. Oh, not half a centimeter, but 1 centimeter. So that's going to be 0.01 meters. And we divide that by the area 2, which is going to have a diameter of 1 centimeter. That'll be 0.005. What is that? 5 millimeters? Meters squared. And then we multiply by V1. And V1 was 1.5 meters over seconds. And the ratio is 4, right? 1 over, this is basically just 1 over a half. So that's basically 4 after you square it. So 4 times 1.5, which is going to be 6 meters per second, as you guys said. So there's V2. The next thing we want to do is to solve for the pressure. That's where we want to apply Bernoulli's equation. And so we can turn this into kind of an equation that looks like this. Pressure 1 plus 1/2 rho being the density of the liquid. This is water, I believe, right? Yeah, water. So times V1 squared plus rho G Y1 equals P2 plus 1/2. Well, that's not a half. Rho V2 squared plus rho G Y2. In order to use this equation, we have to define what y1 and y2 are going to be. We know that the difference in height is 5 meters. I'm just going to say here that we're going to define y2 to be 5 then, because we can, and we'll define y1 to be equal to 0. So we can just cancel out that term right there. And what's left in our equation then is only one unknown, I believe, which is going to be P2. So if we isolate that, we're going to get something like this. P1 plus... So 1/2 rho V1 squared right here is one term. I'm going to subtract that term right there to the left-hand side. It has the same coefficient. And then we'll subtract the rho G Y2. and that's going to be equal to P2. And then it's just a matter of plugging in all the numbers into our equation here. So pressure 1 plus 1/2. What's the density that we're going to use here? Mm-hmm. All right, V1 is 1.5. I'm running out of room here. This term is going to be, okay, we'll put it on the second line. Minus. So rho times G is 9.8. We always make it positive. And then Y2 is 5 meters. Okay, does that look like what most everyone did? I still got a lot of different answers. So some people said 3.34 times 10 to the 5, 3.48. I don't know if those are rounding errors. 2 people said 3.34. Forgot to square the velocities. That makes sense. Easy to do that. Yeah, so what do you guys get? Do you guys agree that if you get 3.34 then? Times 10 to the 5 pascals? Okay. So the answer then is, so this is equal to P2. And you guys are saying that that's 3.34 times 10 to the 5 pascals. That number looks correct to me from having done this problem with my other class. So, what else? Volume flow rate. Okay, volume flow rate means we just take any AV, doesn't matter which one. So if we did, for example, A1, V1, this would be probably the most logical one to do just because this is the information that's given, and we solved for V2, so we could have been wrong. So let's see, area 1 would be pi times 0.01 squared, and then V1 is 1.5. And you guys are saying you got something on the order of, what? Let's see, AV was 1.88. Did anybody else answer for what AV was? 1.88. Let's see if I agree with that. 1.5 times 3 is like 4.5. Maybe it's right, but I'd have to work it out myself. Where's my phone? What do you guys get if you calculate that one? You get the same thing, 1.9? Okay, let's see. Yep, so it's 4 point... What's 9 over 2? Okay, that makes sense, actually. So 4.7... Wait. So I got something completely different than you guys. I don't know. What do you think? Why is that, Cam? Yeah, so the radius, right, would be... Yeah, these physics textbooks, they love doing this. They just love the fact that we're all conditioned to... Yeah, no, I mean, like, we're all conditioned to think of circles in terms of radii, but they love to put things as diameters because they just do. It's every single physics textbook is like this, you know? Yeah. It really used to bother me a lot when I took physics classes. I don't know if it bothers me so much anymore, but it really bothered me when I would spend hours and hours on some problem, and I was just trying to get the answer in the back of the book, you know? And the reason you get it wrong was because of something like that, because you put diameter. It's not a fun reason to spend a lot of hours, but I guess it's an educational moment. If you make those kind of mistakes, to be careful about when you read. Don't make any assumptions. I mean, that's something that I think is relevant for any physics class, is if you're struggling with some problem and you're pretty confident that you're doing it right, that you understand the theory and you understand the method, just take some time to reread the problem carefully, and don't read too fast, because it is our nature when we read things to like. I think especially, I don't know if this is more true now than it used to be, but it feels like everybody has less time because the world is just fast and we are just exposed to so many things that in order to kind of like, what's the word for it? Ingest them, I guess. To read everything, we have to read really quickly. You know, you read through Reddit posts or you read through Facebook posts or Instagram. Well, Instagram's just pictures, I guess, but like you read through like a news post or whatever you're reading, like if it happens to be a physics problem, you're not going to take the time to read every word. You're just going to try to save your time. You're trying to save your time by just reading fast, right? By skimming over it. But the thing with physics problems is they're so short that if you don't take the time to read every single word, these little things will, yeah, it's really easy to miss, right? You know? So, yeah.
Like, who uses Phys for it?
Right, exactly. No, we don't do that, obviously. So, or the, what is it, pi over 6 times d cubed is the volume, I believe. That's something that comes up in Physics 1A. There's a lab you do in Physics 1A where you have to measure the volume of a ball and compare it to the diameter of the ball, and you're supposed to plot it. And students always seem to have such a hard time making the connection between what they're supposed to be, what's the relationship they're supposed to get for the volume versus the diameter. And like every time if anyone's confused, I just ask them, what would it look like if I asked you to tell me what the relationship between volume and radius is? And they all know. But the moment that you throw diameter in there, it's just people are just like, I don't know. D to the fourth? They're just like, who knows? It's just, but it's really natural. I mean, it's the way we've all been taught, right? I mean, all of us have been kind of conditioned to think about circles in terms of radii, right? Is it -4? I think you're right, it is -4. Yeah, you're right. Sorry about that. That's right. This should be a 4. That's 10 to the -4. Thank you, Andrew. Appreciate that. And everybody in the chat was saying 10 to the -4. I should have been smart enough to see that, but I was talking about the problem. Okay, that's your standard Bernoulli problem. Do you guys have any questions at all? You can get quite a few problems in your homework that are like this. Okay, let's do one that I don't know if any of the homework problems from Mastering Physics look like this one. Maybe, but I know for a fact that I gave you a lab manual problem that looks like this, so I wanted to cover this today. So this figure shows a Venturi meter. It's used to measure flow speed in a pipe. We want to derive an expression for the flow speed, V1, in terms of the cross-sectional areas A1 and A2, and the difference in height h of the liquid levels in the 2 vertical tubes. So we've got a tube. I can make this one a little bigger. In that tube, we have one cross-sectional area here that's bigger than A2. The velocity of the fluid basically increases as we move from this point to this point here, V1 and V2, just like in the last problem. The pressures also have to change as well. The one difference here is that above these tubes, you have these columns of water here, right? And one of them goes up to height h. Well, not height, sorry. One of them goes up to some height. The other one goes up to another height. And the difference in the heights here is h, okay? And we want to use Bernoulli's equations, probably along with the continuity equation, to find the flow speed V1 in terms of all of these things, A1, A2, and H. Those are the only things we want to have show up. And I think in our answer, we can also have like density as well. And maybe gravity, that might show up. But other than those, we want to relate them together. All right, again, I want to give you guys some time to think about this one. So take like 4 minutes or so and see if you can come up with something here. I'll go ahead and write down our equation to start with. And of course, if you have any questions as you're doing it, please feel free to ask. There's your starting point, and of course, other than that equation, we've also got the ever so handy continuity equation. does this do? Can I type equations with this? Okay. Okay. I think that was like 3 or 4 minutes. How are you guys doing? Remember, you want to get your answer in terms of only these terms here. A1, A2, and H. And then I said you can also have density show up in your answer. And you could have G show up in your answer. How's that going? You getting close? Mm-hmm. Yeah, how could those pressures be related to each other? What do you guys think? Yeah, true. So Delvino says exactly the same thing, trying to get rid of the pressures. How could you get rid of the pressures? Let's ask another question. What about these two terms? So this is the question about like what does the y1 actually represent? And what you said is certainly a good idea. But what does y1 mean in this equation exactly? Let's look at the previous problem. What did y1 mean in this problem? We said y1 was 0, right? That was because you had this fluid down here. The fluid had to actually go uphill, right? It had to go uphill, which means it kind of loses a little bit of energy, right? And as a result, the pressure gets lower, right? What about this fluid? Does it have to go uphill? It doesn't, right? It doesn't. So y1 basically represents the y-coordinate of the center of the pipe, and y2 is going to represent the y-coordinate of the center of this pipe. But they're at the same level. So in terms of the strict meaning of what these represent, y1 and y2 are both going to be the same, basically. Does that make sense? So y1 here is going to be equal to y2. So that allows us to simplify this and basically just say that these two terms are going to cancel out because they're equal to each other. So again, when you're thinking about this term, you're only going to use it if the fluid has to actually go uphill. Okay, so we're still left with this problem of dealing with the pressures, right? Let's rearrange our equation a little bit here. What do we have? V2 squared. What did you say, Cam? Mm-hmm. What about it? Wait, so you're saying something like pressure 2 is less than pressure 1. Now, if you look at what it says right here, this is basically a hint. Difference in height results from reduced pressure in the throat at point 2, right? So there's less height of water above this right here compared to this right here, right? And I think you kind of said it that the difference between the two has to be basically related to the difference in the amount of water in this column, right? The weight of that water is basically the difference in pressure. And as you said, that's going to basically just be rho times g times h. Right? Does that make sense to you guys? This is kind of a variation of pressure with depth thing that you learned early on, which is that if you have two columns of water, then the water that is higher is going to exert more pressure, right? The deeper you go into a fluid, the more pressure you're going to have. Well, if we assume that, as soon as like the fact that the fluid flows faster here is going to basically reduce the pressure, and that means that the water won't be able to climb as high up the pipe, basically, in this region here, because the water pressure is lower. Yeah. So that means we can just replace P1 minus P2 with rho GH. And then I think all the rows will cancel. We wanted to find V1, right? So we need to replace V2. So V2 is going to be, according to this equation here, V2 is equal to that. All that stuff squared. And now I think even the density cancels out, right? Every term. We're solving for V1, right? So what's left? I'm going to multiply the 2 over here. Factor of V1 squared out. Does that look right? Did I do too many steps at once, or can you guys follow what we just did? think that's the right answer. This is directly from your book, so you can follow what they did in the book, but I think that's the right answer. Yeah. Yep. Okay. Do you guys have any questions? No? Okay. So next we are going to talk about viscosity. Should we take a break before we do this? There's really only 2 other topics for today. We could probably go with no break since it's a shorter class. And these are the only problems we're going to do, unless you guys want me to do more, in which I can. If that's like what I want to do today, basically, I wanted to do these 2 problems, and then we're going to talk about viscosity and turbulence, and then whatever time we have left over at the end. And I also have office hours after this. I'm just going to let you guys ask questions about homework and all that kind of stuff. And if you guys don't have questions, you can go, but that's kind of the idea of what I want to do today. So for viscosity, this is kind of weird because I can start off with like a general idea, but what I really want to do is just kind of, this is going to sound crazy to you guys, I'm sure. We're going to read the textbook together. I'll tell you that viscosity is something like fluid friction in its simplest way. Okay? And I'll tell you that fluids like water have much less viscosity than fluids like honey or syrup. Okay? And to put it in its simplest way, viscosity is this effect that the fluid itself will tend to cling to whatever container it's in, right? You think about the way that fluid flows out of a honey jar, it's going to tend to cling to the sides of the jar. Or if you take a spoon and dip it into honey and take it out, the honey is going to stick to whatever spoon that you pull out of it, right? And it's not going to all fall off. Water, on the other hand, think about take a spoon, put it into a cup of water. You pull the spoon out, there might be a few droplets on it, but most of the droplets of water are going to fall directly back down into the cup, right? You do the same thing with a jar of honey. You put a spoon into there, you pull it out, and the honey very slowly drips off, right? Because it kind of sticks. It tends to stick to its the fluid that it's in, or to the container that it's in. Another example of this would be like a ketchup packet, right? You could buy some French fries. They come with a ketchup packet. You open the ketchup packet, creating a little slit. You turn the ketchup packet upside down. And does the ketchup drip out? No, you have to squeeze it to push it out because ketchup's something that has really high viscosity. Toothpaste also has probably even higher viscosity than these other things. We could go look up what it is, but toothpaste is like extremely difficult to get out of a tube. You know, it won't just naturally fall out. You have to squeeze it. Now, viscosity is something that it's not constant. Meaning the hotter that something gets, I believe the less viscous it becomes in most cases, right? I mean, I'm thinking about, you guys were saying it was really hot this weekend, right? And so I've got a tube of toothpaste that's like sitting upside down in my bathroom. And like my bathroom has a window that's open to the air. And so like when I went to brush my teeth and I opened the thing, the toothpaste basically just fell out of the tube as if it was liquid water or something like that. And that's because it's hot, right? So as these fluids get hotter and hotter and hotter, I believe the viscosity goes down. That's basically viscosity. I have this picture right here, which comes from your book. This is the velocity profile for a viscous fluid. What do you say? Put honey in the fridge, good luck. What happens, Tom? Will it just never come out if you put it into the fridge? That makes sense, because it's going to be really cold. Yeah, okay, that's funny. Never ever. Like, what if you take it out and you put it in the microwave, and then it probably work then, right? Or if you like leave it out to get hot again. So what this is a picture of, and I don't know if this is helpful looking at this picture, but it's saying this is the velocity profile for a viscous fluid. It's saying the pipe has a no. Flowing in a pipe has a parabolic shape. So what they're saying is that the flow near the walls is going to be slower because the fluid tends to get stuck on the walls. And the flow near the front tends to be big. You can think of this as being like something like honey, like slowly dripping out of a vertical container or something like that. What do you need cold honey for, bro? You put it into a pot of boiling water. That would make sense. Okay. So, I don't know. That's viscosity. And there's ways to kind of calculate this. There's ways to talk about this, but your book doesn't really go into detail, so I'm not gonna go into any more detail than that. But I do have the book right here, and I just kind of wanted to do something that I used to do in college. So the college that I went to, what we would do is we would take old texts. Okay, get this whole thing on the screen right here. We would take old texts, like so. When we were talking about thermodynamics, I believe we were reading. Oh man, I don't even know. But when we talked about fluids, you want to guess what documents we read? When we talked about like buoyancy and stuff like that, who did we learn kind of like set up buoyancy, or who like first kind of like figured out how buoyancy worked in this class? Do you guys remember? Archimedes. So we literally read like texts by Archimedes, right? And then when it came to learning about fluid flow, we read stuff written by Bernoulli. Okay, it was just the kind of the way that we did things. So I want to do something kind of similar to that today because I think that it's good to kind of sometimes just actually read things, especially when it's a descriptive thing. So that's what we're gonna do here. We're gonna read paragraph by paragraph. We're gonna like read through this, and I'm just gonna stop and ask if you guys understand what's been written, and we're just gonna have a discussion about what viscosity is. Here's a picture. What's up? I couldn't understand what you were saying, Cam. I'm sorry. Popcorn reading? Let's sit back with your popcorn while we read, yeah. But my goal here is to like actually have you guys ask questions while we're doing this and provide any insight that you personally know as we go through it. Okay. So if there's anything that's written here that you don't understand, like just ask. Okay. So it's really short. There's only like a few paragraphs that we need to read here. All right. Viscosity is an internal friction in a fluid. Does that make sense to you guys? Fluids that have friction. Viscous forces oppose the motion of one portion of the fluid relative to the other. Viscosity is the reason it takes effort to paddle a canoe through calm water. Like as in why it is that the canoe doesn't easily flow through the water. Because there's a drag that's produced on it. But it's also the reason that the paddle works. What does that mean? It's also the reason the paddle works. Yeah. And then Delvino says because the water sticks to the paddle because it opposes the motion of the paddle. That's right. Yeah. If there was no friction, the paddle would just like flow freely through the water. The water would just move out of its way, and you wouldn't be able to go anywhere. Right. A good example of a situation that would be similar is imagine you're sitting in like a rolling chair, right? And you take a paddle and you try to swing it through the air. You're probably not going to go anywhere, right? Because there's just very little force that you can create by pushing through the air because there's very little friction from the air there. Air friction exists, right? But it's the same way in which with no friction, wheels can't turn. That's exactly right, Ruja. You try to spin your wheels on top of ice, they're not going to go anywhere. Same thing if they're in mud. Okay, let's keep going. Viscous effects are important in the flow of fluids in pipes, the flow of blood, the lubrication of engine parts, and many other situations. So this is just indicating why it's important, right? You can imagine situations in which you need to understand how fluids are going to flow through pipes. Maybe you're designing a pipeline to carry gasoline across the country. Flow of blood. This is obviously important understanding like how our heart works and addressing problems with our arteries and stuff like that. Lubrication of engine parts, other situations. So it's important in practical situations. Fluids that flow readily, such as water or gasoline, have smaller viscosities than do thick liquids, such as honey or motor oil. Viscosities of all fluids are strongly temperature dependent. This is what I was saying, what you guys were talking about, that cold honey is going to flow a lot more slowly than hot honey. Let's say increasing for gases and decreasing for liquids as the temperature increases. Wait, so what is it saying? It's saying that the viscosity is temperature dependent, and it increases for gases and decreases for liquids as the temperature increases. So they're saying that viscosity of a gas actually goes up with temperature? Is that what it's saying? Is that how you guys read it? Miara's just like, huh? Gas? I don't think they're talking about plasma. Maybe they are. I know they're going to mention plasma. Maybe is that what you guys think they mean? Is that when it phase changes into a plasma? Increased temperature definitely increases pressure. I mean, what I was thinking was, so what is pressure, right? Pressure is this idea that you have all these molecules around us, and they bombard and impact your skin, for example, and that's how you feel air pressure, right? Is you're literally feeling thousands and thousands and millions of molecules, maybe, that are interacting with your hands as you like wave your hand through the air, or whatever. That's the speed of those molecules that hit you, and as you increase the temperature, the speed goes up. Would you guys agree with that statement? We haven't talked about it yet, but if you increase the temperature of a gas, the molecules themselves are going to have more energy, right? So they're moving faster. And if they have more energy, then they're going to exert more pressure, right? So yeah, that could make sense. The hotter the air gets, you get more resistance against the motion. I'm thinking about this in terms of like the difference of like playing baseball on a hot day versus playing baseball on a cold day. I feel like I've heard people say that they feel like, maybe I'm getting this backwards, that when it's like really hot outside, the ball carries more or something silly like that. Is that something anyone has heard before? Ruja says yes. Am I saying it the right way? That the ball carries more? You've played, and that's the case. You play baseball. That's cool. I wonder how that affects like throwing curveballs and stuff like that. Because you play, well, so it's about the spin yards, but like if the fluid actually becomes more viscous, then it could ride the air more. Like the spin would actually affect it more, right? Does that make sense? That's at least what I'm thinking. Maybe I'm wrong, but okay. I'm just trying to understand this idea that the viscosity actually increases for gases but decreases for liquids, and trying to think of scenarios where I could think about that. The backspin on the ball, it carries a lot more. Yeah, absolutely. Same thing was true of golf, right? Okay. All right, let's see here. Okay, oils for engine lubrication must flow equally well in cold and warm conditions, and so are designed to have as little temperature variation with viscosity as possible. That makes sense, right? If you want to use the kind of oil that's going to keep your engine lubricated, you don't want it to be heavily temperature dependent. All right. A viscous fluid tends to always cling to a solid surface in contact with it. There's always a thin boundary layer of fluid near the surface, in which the fluid is nearly at rest with respect to the surface. This is the idea of like, as you drip honey off of a spoon, it tends to cling to the spoon. All right. That's why dust particles can cling to a fan blade, even when it's rotating rapidly, and why you can't get all the dirt off your car just by squirting a hose at it. Yeah, let's read that again. This is why I like doing this, is because like when you read a textbook slowly enough, like we have all these questions. When you read it fast, you just ignore everything, right? So it says, that's why dust particles can cling to a fan blade even as rotating rapidly. Is that what you're asking about, Miars, or was it the second part of the sentence? And why you can't get all the dirt off your car by just squirting a hose at it. Oh. Are you talking about the ones that like clean off pavement and stuff like that, or just in general? Yeah, but I don't think it's saying that it doesn't. So its claim is that, okay, the first claim is that's why dust particles can get stuck to a fan blade even when it's rotating rapidly. I'm assuming that's because they actually get stuck to the fan. And then it says why you can't get all the. You're asking more about getting the dirt off by squirting a hose at it, and you're wondering how that affects your teeth. Yeah, but you have to do both, right? So like one of them probably gets like a certain layer off, and then when you floss, it gets things that wouldn't be blown off by the water, or something like that. Because people are saying other things. Okay, Biar said boundary layer and how that's related to the second part. How is it at rest or nearly at rest? I was reading that as that. Okay, let me see if I draw a picture right here. What I was thinking that is like, okay, so take a spoon, right? Dip it into something like honey or syrup, right? And our spoon is going to have the honey is going to kind of like drip off of it, right? And you're going to have this like layer of honey that's going to really stick to that spoon, right? And I would say that like while portions of the fluid are moving, like here and here, other portions of the fluid are going to just basically stay at rest. They're going to stick to the surface. Does that make sense? Meower says how it would be at rest. Or nearly at rest. Now eventually these little particles will fall off, but I think the idea is it's like imagine that the honey starts off really thick, right? And then it drips down. These outer portions are going to fall off, but there's always going to be some portion that's kind of near to the surface, I believe. Something like that. Okay. Now, what was the other statement? Why you can't get all the dirt off your car by just squirting. Can't you, though? I mean, I'd say you have to... I guess it makes sense. You have to kind of scrub it a little bit, right? This is like the difference between a water pick and a toothbrush, right? Like a vibrating toothbrush. The vibrating toothbrush has little bristles that help to scratch off food from your teeth, but they also use the motion of the head of the toothbrush inside the liquid in your mouth. The saliva in your mouth produces pressure waves that have wavelengths that we'll talk about later that like squeeze in between your teeth. Is this something you guys have heard of before? Am I using words that are too... Do you guys know how like the Sonicare toothbrushes work? They basically create waves within the saliva. Okay, so when I say Sonicare toothbrush, you know what I mean by that? Like the vibrating toothbrushes? So they basically, like, when you use them, they have two effects. One, you put the brush on your teeth and they literally scrub, right? But another thing that they do is they create pressure waves through the saliva, and the vibration rate of those waves has wavelengths that can kind of squeeze in between the grooves of your teeth and knock out little pieces that the brushes couldn't get. So you need kind of like both of those effects to truly kind of like clean your teeth. But then it's not enough. You also have to use floss to get in between your teeth to scrub those points, right? And then maybe you use a water pick as well to do something similar. But what were we gonna... Okay. This is exactly the same. Yep. Yes. Exactly. Yep. Ultrasonic cleaner. Exactly. That stuff is really cool. Very, very neat. It's interesting, though. I never thought about this as being about viscosity. The fact that you can't get all the dirt off your car just by squirting a hose at it. Okay, let's keep going. Viscosity, unless you guys have other questions you want to talk about. If you do, please chime in. Wouldn't enough... I would think that if you have a high enough pressure... So it says just by squirting a hose at it. Okay, so maybe we can read more into what they mean by that. Maybe the person that wrote this was thinking just a normal hose with pressure. But, like, think about the... I'm sure you guys have all seen these videos of the water pressure they use to, like, clean concrete and stuff like that. Or maybe you've worked at a gas station where you have to clean the concrete off regularly. And those things seem like they can... Like, the super high pressure jets seem like they can really probably get any amount of dirt off, I would assume. But that's what you're saying, Andrew, right? Wouldn't enough... I mean, they're claiming that you can't, but I think enough pressure, you'd probably be able to do it. Pressure washers. Thank you, Isha. I was trying to think of the name of the... They might actually scratch the paint. That's true. You probably also... You guys have seen the videos of, like, the water cutter things? Where it's, like, it's a stream of water, and they use it to, like, cut things in half, like... Silly things, like I saw a video where they were cutting a gun in half with one, and they were cutting, Baron's saying he used to work at a pool with a pressure washer, and it can take a finger off. Wow, that's impressive. Yeah. All right. So viscosity has an important effect on the flow of fluids through pipes, including the flow of blood in the circulatory system. First, think about a fluid with zero viscosity so that we can apply Bernoulli's equation. That's an important part of this little section here, is to know that Bernoulli's equation does not apply to fluids with viscosity. You need a correction to it. If the two ends of a long cylindrical pipe are at the same height, and the flow speed is the same at both ends, Bernoulli's equation tells us the pressure is the same at both ends of the pipe. But this isn't true if we account for viscosity. To see why, and that's what this picture I linked to you guys before, which shows the flow speed profile for laminar flow of a viscous fluid in a long cylindrical pipe. That is a lot of words. Flow speed profile, that's like the rate at which the fluid's flowing. For laminar flow, that means the fluid's flowing nearly in straight lines relative to each other. For viscous fluid, viscous again means it has, think syrup or honey, and then cylindrical pipe. It says, due to viscosity, the speed is 0 at the pipe walls, to which the fluid clings, and it's greatest at the center of the pipe. It's a lot of words. Does that all make sense to you guys? Do you have any questions about those sentences? Speed do be changing next to the walls. Yeah. Arrows get smaller. Yeah, exactly. Because it's getting stuck there. It's like a honey drop, right? That's exactly right, Ishel. That's why the honey clings to the glass as you pour it out. That's right. Yep. That's essentially what viscosity is, that clinging. Okay. We said that we read that? Okay. It says, I like this statement when I was reading this. I thought this was a nice analogy. It says, the motion is like a lot of concentric tubes sliding relative to each other, with the central tube moving the fastest and the outermost tube at rest. Concentric tubes sliding relative to each other. So this would be like, you've got tubes of a bunch of different sizes, and they're all kind of like slightly touching each other, and the ones in the center are going to be faster than the ones on the outside. Viscous forces between the tubes oppose the sliding, so to keep the flow going, we must apply a greater pressure at the back of the flow than at the front. That's why you have to keep squeezing a tube of toothpaste or a packet of ketchup, which are both viscous, to keep the fluid coming out of its container. Your fingers provide a pressure at the back of the flow that is far greater than atmospheric pressure at the front of the flow. Okay? So viscosity just explains why you have to squeeze a packet of ketchup or toothpaste. So this last statement, the last paragraph here is the first place where they talk about any mathematics of this. In general, what they're telling you is that you generally need a lot more pressure with a viscous fluid, right? That's generally what the idea is here. But here they describe exactly how much more pressure. So it says, the pressure difference required to sustain a given volume flow rate through a cylindrical pipe of length L and radius R turns out to be proportional to L over R to the fourth power. So R to the fourth power, that's a pretty big number. Anything raised to the fourth power is going to become pretty extreme. And since it's in the denominator, that means that what does this mean? This means it's going to be harder to squeeze a viscous fluid out of a pipe if the radius of the pipe becomes really small. Does that seem reasonable? The tinier the pipe size, the harder it is going to be to push a fluid through it. So imagine trying to push, imagine you have a syringe full of honey, right? And you try to push the honey out of the syringe. Honey is so viscous that if you try to push it through a tiny little opening, it's going to take a huge amount of pressure probably, right? This would be a nice demo to do. Would be to take some kind of oil. Go ahead. Mm-hmm. Yeah. Yep. Absolutely. That's exactly right. More honey closer to the walls is going to be moving at a very, very slow rate. So it's only the fluid right in the center you're even going to be able to technically push through very well. And there's so little of it if you're trying to pump through a syringe or something like that. I'm sure we probably have a demo of this at the school where you have castor oil or honey and you try to squeeze it through a syringe. I'm sure we have a demo like that. Wish we were at school so we could show something like that. Okay, so it says, if we decrease R by 1/2, the required pressure increases by 2 to the 4th. That's crazy. That's 16 times as much. Decreasing R by a factor of 0.9, a 10% reduction, increases the required pressure difference by a factor of 1.52, a 50% increase. So this relationship, they're saying, explains the connection between a high cholesterol diet, which tends to narrow the arteries, and high blood pressure. Due to the art of the four dependence, and blood is a very viscous fluid, I believe. Due to the art of the four dependence, even a small narrowing of the arteries can result in substantially elevated blood pressure and add added strain on the heart muscle. Okay, that's viscosity. Do you guys have any questions? So I learned a lot today by reading this. I had no idea that... Well, I knew that the viscosity was temperature dependent. I did not know it increased for gases. That's really interesting.
What are practical applications of really, really
I don't know. What do you think? Baron says moat. To have a moat around your castle? Is that what you're thinking? Yeah. If you made a moat full of tar and it was lit on fire too, just to... Could use it for grease and sliding mechanisms. I think that's right, Meowers. That's one of the things I was thinking about. I wanted to hear what you guys thought too. With grease, you kind of want the grease to stay in certain locations on the pieces so that it can produce... So grease is weird, right? Because grease actually has the effect of allowing things to slide. So how is that? How is grease related to viscosity then? I'm kind of interested now. Isn't there a type of oil that was created for less viscosity? For miners deep in the crust. I don't know about that, Ruja. What are you talking about? Maybe so. I've never heard of that. So I was thinking with grease that it sticks to the sides of the walls of whatever you put it in. It doesn't flow. But it also allows things inside to like slide better, right? Too little grease and it causes mechanisms to overheat. Too much grease and it all overheats. Huh? What do you know about this thing, Ruja? Oil that was created with less viscosity for miners deep in the crust. Let him answer. Huh. Okay, so he's saying too much regular oil is too viscous and would clog the pipes, so they had to make a new type of oil so it could flow properly. This is about like pumping things through underground pipes, maybe? Over long distances or something? Yeah, okay. I can see that. So, wait, are you talking about like the difference between like crude oil and petroleum, maybe? Is that what you're talking about? We refine the oil before we send it off at a refinery. That actually makes a lot of sense. I mean, I don't know much about oil processing or anything like that. I just know that there's the oil we pump out of the ground, which is crude, right? Crude oil. And then we process it through an oil refinery wherein it becomes petroleum. Okay, what else? What else is there beyond that? The petroleum can be used to make things like petroleum jelly, but it can also be used to make the petrol that we have in our cars too, right? So maybe that's something like what you're talking about there. Plastics too, yeah, exactly. We also use petroleum to make plastics. All right, I'll let you guys keep typing. Okay, that's all that we're going to do of the reading for today. I hope you guys found that to be useful. I really like doing that when we can. It's just a really short set of sentences here, but I noticed that you guys immediately had questions about what they meant, right? And I wonder sometimes if, like, when you normally read it, if you would even have those questions. Because we don't read that slowly normally. We should. We should read this slowly. Because they say a lot of stuff that forces you to question things, right? And, keep in mind that these textbooks are not always 100% accurate. There's always a lot of little mistakes they make. They try to do their best, of course. Okay, so this is the next topic, turbulence. And we could read what they say here, but I thought we'd do something a little different for turbulence. So I found a video from someone that you guys probably know. Do you guys ever watch this video, this channel? 3 Blue, 1 Brown? Yeah, you guys have seen this before, right? Okay, this guy is just really good, in my opinion. No, I really like his videos. I've watched a bunch of his videos related to mathematics in particular, and he has good physics videos too. So, we're going to watch this video on turbulence. It's about 11 minutes long. I'm also going to link it in the chat, so if you would prefer to just watch it on your own, that's fine. So here we go. But we'll try to watch it through here. I have to do something. I remember the window. Yes, sir. Thank you. I think maybe you're the one that told me that. Okay, that should not require you guys to change the stream, and we should be able to just watch it. He's going to talk about this equation, the Navier-Stokes equation, in this video. This may be something that you talked about in your math classes. Is that something you've heard before? It's not something that I brought up, but he is going to talk about it. If you want to learn more about it, there's places you can read about it. Another good channel, number file. Okay. Let us start this. I just want to pause this right here to mention. Do you guys know who this dude is? Richard Feynman? No one knows. Some of you know who he is. So this guy is, I mean, he's as influential as Einstein. I would say he had the effect of he solved how electricity works at the quantum level, which is referred to today as quantum electrodynamics. It's one of the, or QED for short. It's one of the most astounding theories in all of physics that's been tested to incredible degrees of accuracy. This theory that he wrote down, and it's been shown to be true and relevant in all kinds of scenarios. It's one of the most precise theories in physics we have. There's two things I want to say about Feynman. One is to just notice what he's saying right here. One of the most brilliant physicists of all time says that turbulence is the most important unsolved problem in physics. He doesn't say it's one of the most, he says it is the most important, right? He was also part of the, as Miyares is saying, part of the Rogers Commission that investigated the Challenger disaster. He worked on the Manhattan Project, and I could talk about Feynman for hours. But this is an amazing quote that the video editor puts into this, because I mean, I totally agree with this statement. Turbulence, by its very nature, because it's chaotic, I want to just mention what that means. Chaotic means that he already said it, but I'm just going to reiterate. Very tiny changes to the system will exhibit large-scale effects later on to where it becomes effectively completely unpredictable. Why does that matter? In physics, what we're often trying to do is to predict things, right? We create a model, we look at the initial state of a system, and we want to be able to describe over time how that state evolves, right? A simple example of this would be the motion of the planets. If we know where the planets are at any moment in time, which we kind of do, right? We can predict over time where they will be thousands and thousands and thousands of years into the future. And okay, and you're mentioning that Pluto is known for having chaotic motion. I didn't even know that, Miyares. That's actually really interesting. But the other planets, we believe we can predict exactly where they're going to be over time. And that's an example of a predictable model of physics that has been very powerful in terms of making predictions. When it comes to turbulence, right, we can't predict things. That's the whole problem, is it's chaotic. It breaks down our ability to actually predict from moment to moment what's happening. And examples of this are things like the weather and things like hurricanes and stuff like that, right? You know how sometimes they'll say a hurricane is going to hit someplace, but then it gets closer and then due to just random motions ends up kind of completely bypassing and goes back out to sea? Now, I know we live on the West Coast, and maybe this isn't so important, but if you live in Florida, if you live in the southeastern United States, or you live in like Washington or anything like that on the East Coast, you have to deal with these predictions that a hurricane's going to come in and have a big effect on your community. And sometimes it just doesn't, and sometimes it's way worse than they predicted, right? And this is why we can't predict the weather. Like if we could truly understand turbulence, we could predict the weather in a much more accurate way, and we'd probably be able to control it. And I think that's a really powerful idea. If we can control the weather, I mean, maybe I'm going too far off the deep end here or something like this, but it's certainly the first step. If we can come up with a good way to understand turbulence from a mathematical. You said one other thing, Meow, just saying you believe it was the reason why chaos theory became a legitimate branch of mathematics in the 60s, or something according to my math professors. That sounds right to me. Yeah, the study of chaos is a big part of mathematics in the same way that turbulence, which is an example of chaos, is studied in physics. So I'm gonna go ahead and push play again. But there's someone typing. I might wait a second. To major in chaos. Yeah. Yeah. Okay. What do you guys think? Do you have any questions? Are you on board with how difficult of a problem it is at the very least? That's all I wanted to kind of expose you to, is just how complicated of an issue it is to kind of predict these type of situations. There'll never be an aerodynamicist. Yeah, I could never do this. Stuff like this is too complicated for me. And I remember studying chaos theory when I was in undergrad, I think, and thinking, like, I don't like systems like that. Do you guys know about the double pendulum? He was using it. Turbulence is basically a bunch of eddies getting smaller and smaller. Well, that seems to be the way he's describing it, right? Is that you start off with these larger eddies and they kind of dissipate into smaller eddies. A lot of random motion. So this is the simplest example in physics. Is it still showing my screen? Okay. So this is called double pendulum. It starts off and it's just a normal pendulum, right? But then he loosens the thing in the middle. I don't know if we have one of these at our school. I can't remember. That is chaotic behavior right there. That's chaos. Meaning that we can't... Okay, so a pendulum's pretty simple, right? But as soon as you have a second pendulum on top of the first pendulum, I mean, it looks chaotic. Would you guys agree with that? It looks pretty chaotic. So we can't solve this system. We can't predict what it's going to do because little tiny changes can alter the way that the system behaves. Look how long it's going too. I mean, it's just crazy. Sometimes it'll flip around, but like you can't really predict when it will, and then all of a sudden it's just flipping around like crazy. So yeah, this is something we study in physics to exhibit like how complicated systems can get. That thing is really going. Is there 3? You could have a third one if you want to. You could add a third one to the end. Yeah, double pendulum. It's pretty cool. I was watching a video by this guy named Sean Carroll, who's a physicist from Caltech, and he basically had little lights on these things, and like turned the lights out and like showed how it just looks really cool. How does the Navier-Stokes equation work? That's something I haven't really studied at all. I mean, we could read about it. I noticed within the equation that I recognize some of the parts of it, but that doesn't mean that I understand anything about it. Let me see here. So it's got a continuity equation. What does V represent? V is going to be fluid velocity, probably, right? Local acceleration. Yeah, it's fluid velocity. So this says the divergence of the fluid velocity is 0. What does that mean? You guys have taken 220, right? What is divergence? So this is divergence, right? 220 was a blur. It's hilarious. What I would say is that if I was to take a small box of the fluid, here, let me switch back to sharing screen. Change windows, screen 1. So I believe what this says, this continuity equation says, the divergence of the velocity vector field is 0. You remember curl? I can explain divergence pretty well, I think. So imagine that I've got a fluid. Okay, this is just going to be me completely. And let's say that you've got all these different velocity vectors for the fluid. So you've got, one's moving this way, so each of these are going to represent velocity. Okay, each of these vectors. So you got some that are going this way, some that are going that way, right? What that first equation states is that if I was to take a box, a cube, and I was to put it around this object right here, that basically just as much fluid would flow in as would flow out of my box. Does that make sense? That's what this means. just as much fluid flows in as flows out. Does that seem reasonable? There's no preferential flow. Okay. Now, what I'm wondering is, how does that apply if you've got an external force affecting the fluid? Like what if you have an external force that's pushing this way? Right? Wouldn't that make it so that the fluid would tend to flow through the box? So maybe there's some certain conditions that they're giving here. Maybe the conditions of the Navier-Stokes equation are something like for an enclosed fluid that's not subject to forces or something like that. I don't know. But that's one of the equations, I guess. And then the other one, this is something you'll look at. This is something you're going to look at in Physics 1C. But instead of having a velocity field, you're going to have the electric field or the magnetic field. And then this one, as he was describing, is basically F equals ma, right? With the right side being forces. Some of the forces are going to vary as the second derivative of the velocity. This is like the gravitational force. And then the pressure gradient. So if there's any change in pressure, it's going to affect the velocity of the fluid. And then this is just trying to tell you how the velocity of the fluid changes with time, right? So if I was to read this in words, what this equation would say is that the acceleration of the fluid, right? dV/dt is acceleration, right? The time rate of change of velocity, multiplied by density. So density times acceleration is equal to the way in which the pressure is changing. That's what this says. A pressure gradient says the rate at which the pressure is changing spatially. So certain regions of space, maybe the pressure is changing very rapidly. If the pressure changes really rapidly, it's going to have the effect of causing the fluid to accelerate. That's what that says. And specifically, it mentions here that fluid flows in the direction of largest change in pressure. That's similar to the way, what's something we can compare this to? A ball on a mountain. Imagine a ball flowing down, like rolling down a mountain. The direction the ball is going to fall would be the direction in which the elevation changes the most quickly. Would you guys agree with that statement? A ball falling down a mountain, the direction it falls is going to be along the steepest point, right? So this is the same idea, but just with pressure, because with fluids, you got to talk about pressure instead of talking about forces, right? Okay. So the place where the pressure changes the most is going to be the direction the fluid flows, i.e. the direction the fluid accelerates in, the way it moves, right? So pressure is going to affect the way that it moves. In addition to that, there could be external forces, such as gravity, pushing down on it. So you could have a term like this, that gravity may pull the fluid down as well. So it could be not only pressure that's affecting the motion of the fluid, but also gravity affecting the motion of the fluid. But in addition, the fluid has a self-interaction term, meaning that it interacts with itself, i.e. viscosity. That's what this term represents right here. Now, what is mu? I wonder what mu is. Yeah, something like that, probably. Mm-hmm. Yeah. And then Nobel squared is basically the second spatial derivative of the velocity. Viscosity acts as a diffusion of momentum. Okay. Diffusion term. Okay. Anyway. Yeah, this is a total derivative, so it has a spatial component and a time component too. Boy, here's a bigger version of it if you like to look at the full version. Well, math is fun, isn't it? Is that an equation you guys talk about in your math classes? I know you probably talk about like Stokes theorem in your math classes, right? Or not is that right? Stokes theorem?
Yeah.
That relates a volume integral to a surface integral, like a closed surface integral, I think. Is that Stokes theorem? Or is Stokes theorem the one that relates the line integral to the and I never remember off the top of my head which one it is. Gauss's theorem, I think, is the one that relates the 2D to 1D. And then Stokes theorem is the other one? I can't remember. I can pull up some of my books and figure it out, but Okay, I think I'm gonna stop the recording for now. But like I said,